In this video, we will continue our review of probability, starting with the definition of intersection. So this is going to be the set of events common to A and B, or actually B and C in this picture. So the common region is the overlapping region between the two sets. So the B intersection with C, that's the symbol down here, this horseshoe symbol, is the set 7, 9 in this example. So if I was to reach into this universal set and pull out a number randomly, what are the chances that it would be in the intersection region? That would be the probability of B intersection C, and that equals 2/10 here because there's two things in the overlap and 10 numbers overall. So 1/5 or 2/10. The union of events B and C is going to be the event containing all outcomes that belong to B or C or both. So B and C both come to the table and bring everything that they have. The union of B and C here would include the 1, the 3, the 5, as well as the 7 and the 9, and the 6 and the 8, which that set contains 7 numbers, so the probability of getting something in the union of B and C here would be 7 out of 10 altogether in the universal set. You may have to use Venn diagrams in problem solving for probability questions. Here's a group of 30 students, so the universal set has 30 students. 17 play computer games and 10 play board games. We don't know how many students played both, so some of those 17 and 10 might be in the overlap region, and we're not sure how many. 9 students play neither. Draw a Venn diagram to show this information. So at the start, you're going to want to draw a Venn diagram that has an X in the overlap region. And then you can conclude or deduce that the region in the computer games circle must be 17 minus X, because the X from the overlap region would not be included in this region here. And the board game circle is going to be 10 minus X. And 9 students out here in the universal set that play neither game. So then each of these distinct regions sum together to equal 30, which is the total number of students in the universal set. You can then solve that equation and figure out that X equals 6, and then you can fill in the rest of the Venn diagram accurately. Knowing that the overlap is 6, there must be 11 who play computer games exclusively, and 4 who play board games exclusively, and then the 9 that are on the outside. So then we can answer probability questions from our complete Venn diagram. So question A says, what's the probability that a student chosen at random from the group plays board games? Well, that includes the 6 people in the middle and the 4 people who play exclusively board games, so 10 out of 30, which reduces to 1/3. Question B, probability that a student plays both computer games and board games. We know those are the 6 in the center out of 30, and notice the notation I used here is the intersection of C and B. And then part C says probability that a student plays board games but not computer games, and that's these 4 folks who play exclusively board games, so 4 out of 30, which is 2 out of 15. And if you look at how I wrote that symbolically, that's the probability of board games, the entire circle, minus the overlap region, and so that gives us just the 4 out of 30. The addition rule for any 2 events, A and B, is that to find the probability of getting something in the union of A and B, you know that means something from either the A, the B, or the overlap region. You can add the probability of A to the probability of B. And then you'll have to subtract the overlapping region once. The reason being, when I add the probability of A, it includes the overlap region. And so when I add it to the probability of B, it would include the overlap region again. And so I don't want that overlap region to double count, but I do want it to count once. So since it's already in the probability of A and B, I'll just subtract the overlap region's probability one time, and that'll be the overall probability of the union for A and B. So for example, we have a card that's drawn at random from an ordinary pack of 52 playing cards. So you will have to know that there are 4 suits in a deck of cards: hearts, diamonds, clubs, and spades. And you'll have to know that there are the numbers ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, and queen. And here we're asked to find the probability that the card we draw is either a heart or a king. So you can think about that as the union of hearts and kings, right? So here's our probability formula for union of 2 events. Here it is translated into deck of cards symbols. So the heart or king, that's how you can read this union symbol, right? Like the word or. So what's the probability of reaching in and pulling out a heart or a king? Well, it's going to be the probability of getting a heart plus the probability of getting a king. But that's going to double count the overlap region. You'll have to subtract the overlap region of heart with king. What this ends up looking like is the probability of getting a heart is 13 out of 52, because there are 13 hearts in the deck, plus the probability of getting a king which is going to be 4 out of 52. But then I will have to subtract the card that got double counted, which was the King of Hearts itself. So I'll have to subtract 1 out of 52. And then this ends up being 16 out of 52, which reduces to 4 out of 13. You may be asked to do a purely symbolic probability question, so there's no story behind this. They're giving us two events, A and B, telling us the probabilities of A and B. We don't know the overlap region. We are told this extra piece of information that the probability of the union is equal to 2 times the probability of the intersection. So if I was just to set up the only formula we have to work with here that involves all of these various variables, I could replace this union of A and B probability on the left side of the equation with the thing that they told me it's equivalent to, which is 2 times the probability of the intersection. And that would look like this. Meanwhile, I'm also replacing the probability of A with 9/20ths and the probability of B with 3/10. Now you can see we only have one variable remaining. It's on both sides of the equation. It's the probability of the intersection of A and B. There's 2 of them on the left and there's -1 of them on the right. And so I can add the one from the right over here to the left. That'll give me 3 probability of intersection A and B equals 9/20 plus 6/20. I just gave that a common denominator. And then I'm going to solve this equation for the probability of the intersection of A and B. So you're sort of treating that whole expression, probability of the intersection of A and B, as your variable to solve for. And so that ends up being 1/4. So if the intersection's probability is 1/4, now I could sketch this thing in a Venn diagram. Let's see if I do that next. Oh, no, I'm not going to do that till the last question. All right, let's see if I can answer this series of questions at once. For part A, it said, find the probability of the union of A and B. All right, so far what I've solved for is the intersection. How can I use that to find the union? Well, in this problem, it tells me specifically that the probability of the union is equal to 2 times the probability of the intersection. If I take 2 and I multiply it by 1/4, I will get 1/2, and that's the probability of the union of A and B in this question. Question B is asking me for the probability of the union of A and B not with this little prime outside of it. It means the complement of the union of A and B. So basically 1 minus the union probability. So 1 minus 1/2, which gives me also 1/2. So basically this means half of the things are inside the union and half of the things are outside the union. That's what this probability shows. And then part C is a little bit more complicated. If you look at where the prime is, it's showing us the probability of the intersection of A with not B. So the probability of the overlap region between the A circle and the things that are not B. So if you think about that on a Venn diagram, it's going to be the region I have shaded blue here. So the probability of being in the intersection of A with not B, and that's just going to be this blue area here, for which the probability is 1/5. Now the way I got 1/5 was to know that my original A probability was 9/20, and the overlap I had solved for was 1/4. So when I did 9/20ths minus 1/4, I got this 1/5 here in the A circle. Another definition to know is about independent events. So 2 events are independent if knowing that one of them occurs does not change the probabilities for the other event occurring. So this would be like if I was to roll a dice and toss a coin at the same time. Those are going to be independent events because getting a 6 on the dice doesn't mean that I am changing the probabilities of what's going to happen on the coin, right? However, if I was, let's say, pulling a sock out of a drawer and then reaching back into the drawer to pull out another sock without ever replacing the first one, well, then I've changed my probabilities for the next scenario. So those events would be not independent. Simple multiplication rule for independent events in probability is that if the 2 events are independent, then when I multiply their probabilities, I should get the probability of their intersection region, or the probability of event A and B both happening. If you're asked to determine if 2 events are independent, you're just going to want to check if this formula holds up. So is it a true statement based on the probabilities given in the question? And if the left side and the right side are not equal to each other, then they're not independent events. If the left side and the right side are equal to each other, the true statement, then the events are independent. Here's an example of just some probabilities. Bag containing 1 red and 4 white balls. So these are independent events if I'm going to select a ball at random from each bag, because what happens from the first bag is not going to have any impact on the probabilities for the second bag. So we can consider these independent events, which means if I'm looking for the probability that both balls are red, I can multiply their probabilities together. based on the formula that we just saw, the multiplication rule for independent events. Or you can think about this as a tree diagram. You can select a ball from the first bag, and then the branches continue for the second bag. So the probability of both balls being red would be like a red from the first followed by a red from the second. It's going to end up being 3/5 for the first bag, 1/5 for the second bag, because there are 5 balls, but only one is red. And so I can multiply those together and get 3/25. So this is sort of like doing a tree diagram without the tree diagram. I'm just applying our straightforward multiplication rule for independent events. Probability that the balls are different colors. So this would be a red followed by a white, or a white followed by a red. So we have to sum together those two pathways, right? Red followed by white, or white followed by red. So that's 14 out of 25 altogether. And then finally, the probability that at least one of the balls would be white, which means I've got 3 choices: red, white, white, or white, red. But rather than summing together 3 different probabilities, remember you can also think about at least one as being the complement of none. And so it's going to be 1 minus no white balls. And since no white balls is the same as saying 2 red, it's just 1 minus our answer from part A, which ends up being 22 out of 25. And then one more simple independent events question. Probability that you find a certain traffic light green on your way to work is 30%. No matter the day, 30% of the time, the light's going to be green. So what's the probability that you find it green on 2 consecutive days? Well, if it was green today, has no effect on what's going to happen tomorrow, right? Those are independent events. So I can just straight multiply the probability. So probability of today is 0.3, probability tomorrow would be 0.3. I can multiply those together and figure out that the probability of getting it 2 days in a row is going to be 0.09. And that is all.